So here we are in video 4 of the electrochemistry chapter, and this time we're going to talk about the electron moving force. So in our lemon battery, we have right now a current voltage of 0.64 volts, but like I did before, if I replace this with a different metal, like for example zinc, I can see that my voltage is actually different, because there's a different want for electrons between these two metals. And that amount of want, or that amount of desire, or that amount of possibility of gaining electrons is what we're going to talk about today. So section 20.4 is called cell potentials. And at 25 degrees Celsius in 1 atmosphere of pressure and in 1 molar solution, which are called standard conditions, we know that electrons are lost from zinc and they flow through the wire to the copper, and then the anions go through the salt bridge back to the anode. That's what we learned in the past. But why does it flow from zinc to copper? Why is copper more attractive to electrons than zinc? Well, the electrons move spontaneously due to potential energy. Potential energy of copper having the possibility of being reduced more so than zinc. This potential is also known as the possibility, the ability to be reduced. And this ability to be reduced means the ability to gain electrons. And copper has a greater ability than does zinc. This ability to be reduced is actually something that is not unique to just copper and zinc. It happens to everything. And everything has the possibility of being reduced, or the potential of being reduced, that's different from everything else. And these possibilities or potentials to be reduced are ranked. The ranking system that shows these is called a standard, because we're at standard temperature, pressure, and molarity right here. Standard possibility of reduction. It's called a standard reduction possibility. And they put them at 25 degrees Celsius in 1 molar solution. And in your textbook, there's a huge list right here of the possibilities of things being reduced. And they rank them in something called volts. And you can see right here that this one has the possibility that's associated with 2.87 volts, all the way down here to negative 3.05 voltage. The ones that are negative have a really good possibility of being oxidized. The ones that are positive are the ones that have a really good possibility of gaining electrons. And you can see on this chart that copper has a positive 0.34 possibility of gaining electrons, whereas zinc has a negative 7.6 possibility. And since zinc is lower, that means it's going to be oxidized in comparison to copper, which will be our species that is reduced. This ranking scale of possibly being reduced is known by at least 6 different names. It's known as the more positive, the more possible of being reduced, and the fancy names for these are the ones that you'll find in textbooks, on tests or quizzes, is the reduction potential, or the potential, the possibility of reduction happening to it. It's also known as the voltage, because that's what it's measured in, is volts. The reduction potential is measured in volts, symbolized by the letter V. By the way, a volt is equal to a joule per coulomb, for those of you that are like super interested in the units. It is also known as the electron moving force. The fancy name is the Electro-Motive Force, because it's the force that pushes electrons or pulls electrons from one place to the other. Since electromotive force is a lot to say, sometimes we just call it the EMF for EMF, electron moving electromotive force. Since EMF is even difficult to write all three letters, lots of times we just write E. And sometimes we'll put a little circle in the upper right-hand corner, and the circle means that it is at 25 degrees Celsius, 1 atmosphere, 1 molar. It's at standard conditions. And remember, it's called the standard reduction potential because of these conditions. And so getting used to all of these names or all of these words of saying which one has the most possibility of being reduced is sometimes a mouthful. And so just calling it the E is sometimes just the easiest. The E, the electromotive force, the reduction potential, the standard reduction potential. So how do we know where these are? And as a matter of fact, it's arbitrary. There is a 0 in here, defined as a 0 ability to gain or lose electrons, is called the standard hydrogen electrode. And you can see it right here. H plus 2 electrons goes to H2. That's the standard hydrogen electrode. And it's symbolized SHE, a She, standard hydrogen electrode. And if you want to write the equation down, it's 2H plus aqueous plus 2 electrons goes to H2 gas. And so this is the standard that everything else is based off of as far as how much something wants to gain electrons or lose electrons. Now, before we go on and do a little bit of math with this, let's just take a look at a voltaic or galvanic cell. And let's look at a voltaic or galvanic cell that has a standard hydrogen electrode so you can see how it practically works. Here's our zinc electrode again, just like we had in the last video, where zinc would lose electrons and then they'd go through the wire to the load right here, and then they'd go over here. And in this case, instead of being copper, this is a cathode compartment called a standard hydrogen electrode, or a She. And in this case, it's got hydrogen gas being added to it, and then it has an inert electrode called platinum that doesn't gain or lose electrons at all. It just allows the electrons to move off of it. And then we can see that hydrogen ions right here would be reduced, forming more hydrogen gas. And then we can see that the anions flow through the salt bridge back here to the anode. So that's what a standard hydrogen electrode illustration would look like. There is a much greater standard reduction potential, or E ranking, in Appendix E of your textbook. And in Appendix E, they have hundreds of different half reactions that give you the standard reduction potential, or the voltage, or the E circle, the E with the little circle. And this is in the back of your textbook in Appendix E. We'll refer to that when we're doing lots of problems. So the trick with this is to calculate the difference. Calculate the difference between zinc's possibility of gaining electrons and copper's possibility of gaining electrons. And when you calculate that difference, you now know the voltage, or the volts, or the standard reduction potential between those two. And you know how good your battery is going to be at attracting the electrons from one place to the other, and how much useful electronage you actually have. AKA, this is known as the E, or the electromotive force, of the particular cell, or galvanic cell, or voltaic cell, or if you just want to call it a battery, that's okay. To find this, you always take the cathode's standard reduction potential, the one you find off of here or off of here, and then find the difference between that and the anode. Difference in math class, of course, means subtract, and so that's why there's a minus sign right there. And so let's look these up for zinc and copper. And zinc, I think I pointed out to you before, is negative 0.76, so that's our anode. And then copper is positive 0.34, and so that's our cathode. How do I know which one's the cathode and the anode? Remember, the more positive one is the one that's more possibly reduced, and reduction is the cathode. You can remember that by red cat, because the more reduced possible one is always the cathode. So up here, half reaction, potential, positive, negative, negative 0.34, minus a minus 0.76, we should get about 1.1 volts. And as a matter of fact, I'll pull my lemon battery up. We're getting a little bit more than that right here for my copper zinc one, probably because I'm not exactly at the standard conditions. I'm not exactly at 1 molar solution. It's a little more concentrated in here. And I'm not exactly at 25 degrees Celsius. So that can vary a little bit. But this is what the standard voltage would be. And the volts, remember, are measured in joules per coulomb, or also known as a volt. So let's do a couple of quick examples. First of all, here's an here's a redox reaction that could act as an electrochemical cell or as a battery. And let's find the electromotive force, or the voltage, of this cell. First of all, we can look at this reaction and decide right now which thing is oxidized and which thing is reduced. And I see nickel goes from 0 to +2, and since that went up in charge, that's going to be oxidized. Silver is +1 here and 0 here. It goes down in charge, therefore it's reduced. And remember, red cat, whichever one's reduced, that's going to be my cathode. So silver is my cathode. And you can also remember anox. Anode is oxidized, so red cat and ox will help you decide which one to put where in each of these. So let's look up silver now as my cathode. Silver is right here, it's 0.8. And then let's look up nickel. Nickel's down a little ways on here. Nickel is right here, negative 0.28. And so we put in 0.8 right here for silver, and negative 0.28 for nickel. Remember, it's minus a minus, and so we should end up with a battery with a voltage of 1.08 volts. Let's do one more example. In this one, I'm going to turn the question around. Let's say that we have a battery, and we have a voltage of the battery of 1.46 volts, and it's got these two half reactions right here. Indium goes to indium +3 and 2 electrons, and bromine plus 2 electrons goes to bromine minus 1, 2 of those. Okay? Now, from this, please calculate the standard reduction possibility for indium. Notice indium's not on this list right here. I don't think it's even in Appendix E in the back of your book. And so now we're given this, and we're also given bromines, or we can look up bromine on here because bromine's a pretty popular one. We can find it right here as 1.06. But what is indium? So we're missing one piece from this equation. All right, let's just make sure we know which thing is the red cat and which thing is the anox. Well, bromine right here is a positive 1.06, which is pretty high as far as voltage goes. So we're going to make that assumption, since it's way up here, that that is going to be our cathode. And so we would take 1.06 as our cathode minus our anode, and then that's going to equal 1.46. And since we want to know x right here, we would subtract 1.06 from both sides. Remember that there's a minus sign right here. Change the signs, and then x would equal negative 0.40, and therefore our E of indium at standard conditions would be negative 0.40 volts. And that would fit right here around where iron is, or right between iron and nickel on the standard reduction potentials list. Good luck with your EMF standard hydrogen electrodes and calculating the E cell, known as the EMF, the electromotive force, the volts, the standard reduction potential, or the possibility of being reduced in volts.